Hi everyone, hope you're doing good. In this video, I'm going to explain how to implement the optimal allocation of EV charging stations and DGs on Ieee 33 distribution network. Well, placing EV charging stations on buses requires to monitor the power loss and voltage deviation. So it's crucial to use optimization method to determine which of these buses are a best place for the EV charging stations. So as I said, monitoring the power loss and voltage deviation is really important in this project. After placing the EV charging stations, we place 3 DGs into the system in order to reduce the power loss and also improve the voltage deviation. Any EV charging stations come with different configuration. It can have different type of chargers, including type 1, type 2, and type 3. Type 1 is the slow charger and type 3 is the fast charger. In the Matlab code, we have a test that will perform the entire project. But before that, let's check the configuration for the EV charging stations. Well, in the first section, you see the charger data. We have 3 type of charging points, and each of the charging points have different output power. For the first one, which is the slow charger, it has 1.44 kilowatt power. The second one is 11.5 kilowatt, and the last one is 96 kilowatt of power. So this is my configuration. So for this project, I'm deciding to have 10 of charging point 1, 2 of charging point 2, and 1 charging point 3, which is fast charger, into the first station. For the second station, I have 8, 4, and 2 charging points, respectively, from 1 to 3. And here is the configuration for the other EV charging stations. And in total, we have 5 charging stations, and the configuration is visible for you here. So before running this, let's just clear the command window and run the first section. Here we have the charging data. Then we have the info of EV charging stations. In here, we are basically accessing the information and calculate the real power and reactive power loss based on the power factor, which is defined as 0.85 in this project. So by running the third section and looking at the PS underscore EVCS, we can see the real power data, and also we can check out the reactive power loss. 133.4 kilowatts is the power for the first charging station, and with the reactive power of 83.6739, the real power and reactive power of other charging stations are also calculated and determined here. The configuration of EV charging stations in this project are same and they're not changed. Let's clear all command window and let's go to the test file. All right, so we're going to have 5 EV charging stations and 3 DGs into our case study distribution network, which is Ieee 33 bus. And for the DGs, we're going to consider the location and size. The load flow analysis would be backward forward sweep, and this is the configuration and information of EV charging stations as we explained earlier. So we have 4 tests in this project. The very first test is just to know to apply the power flow analysis over the Ieee 33 network. And in this test, we don't consider any EV charging stations or DG. We just want to find out what is the power loss, real and reactive, the voltage deviation, and minimum and maximum voltage. In the second test, we're going to allocate the 5 EV charging stations into the system, but still we do not care about adding any DGs. We want to see what's the output power, power loss, and etc. So the third test will consider the DG locations, but still will consider the constant sizes for DG. We don't let the PSO method to determine the size for the DGs, and we'll monitor again for power loss, voltage deviation, and minimum and maximum voltage. In the fourth test, we're going to consider the EV charging station locations, DG location, and sizes. So we let the system to determine the size. The first test gives us this information. As we can see, the power loss is almost 202 kilowatts, and it's almost 202 kilowatt, yeah. And the reactive power loss 134.74, and the voltage deviation is almost 11.64%. Minimum voltage is 0.91, and a maximum voltage, which is for the slack bus, the first bus, it would be 1 per unit. So if you go into the second test, you will see that the best locations for the EV charging stations are determined at 2, 3, 6, 7, 13. There's explanation for this, and I'll explain this one at the end of this video. So for this section, we're going to determine the population of the IPSO to be 250, and the iteration would be 50. The number of EV charging stations would be set to 5, and there is a test limit here which we set it to 1, and I'll explain you at the end of this video why we have the test limit. For now, we just keep this one at 1. So, and we also we can determine we can consider different number of EV charging stations like 3, 4, 5, but for now we just keep it at 5, and we want to see what would be the best recommended locations of EV charging stations by the system. When you run this section, you basically get the iterations and best cost. So the best cost that shows you a value, which is the summation of the power loss and the voltage deviation. I'll explain you this part also later on in this video. So we're just looking at the number, and our goal, or the goal of the PSO, is just to reach the minimum value as the value should be as minimum as possible. So the iteration is reaching to 50, which we set it right now, and we have the summary of the results. As you can see, the fitness value tends to reach to the lowest as possible. So for the first trial, it was 438, and then it reduced to 432, and at the end it reached to 432. So there is no unit for this because, as I said, it's just a summation of power loss and voltage deviation. When we look at the results, we see that the first table shows the information of EV charging stations used for this study. So we have charging point 1 with 1.44 kilowatt, second one with 11.5 kilowatt, and the third one with 96 kilowatt. And this configuration for each of these EV charging stations gives us the power loss, the total real power and total reactive power. So for example, for the first one is 133.4 as the real power for the first EV charging stations, and the reactive power also is visible. So with this configuration, the best locations are reported as 2, 3, 6, 7, and 13. So that means the first charging stations can be placed as in the bus 2, the second one can be placed in bus number 3, and the third one can be placed in bus number 6. The fourth one can be placed in bus number 7, and the fifth one should be placed in bus 13. With this configuration and with this allocation, we can have this table shows the voltage profile of the system. So with these locations for the EV charging stations, we can have 0.86 as the minimum voltage, and the voltage deviation is 25.401. So we can see that the real power loss increased because we have added the load to the system. So now the real power loss is 407 and roughly, and the reactive power loss is 273, which compared to no EV charging stations, we can see that the power loss increased drastically. So now I think you understand why we need to add DGs in the system. But let's go first explain about the IPSO. And in the IPSO, we see that for the DGs, we have a limit. Okay, so the limit for the total DGs used for the system cannot exceed 2000 plus 10%. That would be like 2000 plus 200, or 10% of 2000 would be 200. So that would be 2200 kilowatt. That means the total size cannot exceed 2200. This is the limitation for the IPSO. And we have to place 3 DGs in the system, right? So the maximum DG size says that the DG size, individual DG size have to be within that boundary from 2000 to 50. So the IPSO will basically go through the first iteration, and then it goes through the main loop, which basically starts from the first iteration until the last iteration we defined. And in here, you can see the entire code that will allocate the DGs and EV charging stations for our system. So in here we can see how the DG size is being determined, selected, and all this part that you can see is basically written for the DG size and location. So furthermore, we can go ahead and see the load flow. I'm not sure if you can. Oh yeah, I found it. So the load flow, it has some parameters there, and the first one determines the bus the bus type. I mean, a bus system is 33 actually. The P is the location of the EV charging stations. The number of EV charging stations would be 5 in this case. The DG and number of DGs used in the system are the fourth and fifth parameter. Optimal size determine whether we want to have a size or constant size for DGs, and DG size basically gives the information of size of DGs. So because we don't have DG right now in this code, our system is just considering the 5 location for EV charging stations and determine the location for them. So as you can see, the DG size and DG locations are set to 0 in this case. So if you go to the load flow, in the load flow file, we apply the loads and also DGs into our bus, and we get the fitness value at the end. This is the load flow analysis based on the forward sweep, and at the end what we are interested in is the fitness. The fitness is the summation of the real power loss and the voltage deviation. The voltage deviation is found using this equation, and by summing the voltage deviation and the power loss, we can get the fitness value. And our goal is to reduce the fitness value as much as possible. As you can see here, the fitness is 432.4796, which basically is the summation of real power loss, which is 407, plus the 25.41 as voltage deviation. So the goal here is to reduce the power loss and the voltage deviation. All right, so we go back to the main test file, and test 2 is done, and we already know that what are the best locations for EV charging stations. Now in test 3, we're going to reduce the power loss and the voltage deviation by adding DGs into the system, but we do not allow the IPSO to determine the size in this case. We define the population to be 50 and iteration to be 100. So, and the number of EV charging stations stays as 5 in this case. And now we do not let the optimal size to be true, because we want to have constant sizes. And the number of DGs for this test is going to be 3. You can go ahead and select any number of DGs you like. 1, 2, 3, maximum 3 DGs are allowed in this project. So by selecting the number of DGs to be 3 and running the test 3 sections, we can basically see that the IPSO is basically looking for the best cost. Now you can see that the cost, which is the fitness of the IPSO, is drastically reduced. In test 2 we had 430 something, but now it's 137 with adding 3 DGs. Later on I'll explain what are the sizes of DGs. For now, table 1 is same as the previous tests. We let the system to have the locations of EV charging stations as it was in test 2. 2, 3, 6, 7, 13 are going to be the locations of EV charging stations, and the IPSO determined that the best DG locations could be at bus 6, 13, and 7 for the first DG, second DG, and third DG. And we can see that the power loss is reduced drastically. Almost 276 kilowatts of power is saved right now. And in terms of percentage and power loss reduction, compared to no DG, we have 47.9% improvement. When we look at the voltage profile, we can see that the voltage profile right now is better. It's 0.93 is the minimum voltage. Previously in test 2 it was 0.86, and now the voltage deviation is drastically reduced from 25 to 6.74, and this means that the voltage deviation is reduced by 18%. Right, so this means that the improvement in terms of voltage deviation was 73%. And when we look at the power loss, we definitely see that the power loss is minimized. 130.43 kilowatts is the power loss right now with adding those 3 DGs, and the fitness value is clear. So now that we have used constant sizes for DGs, let's proceed and allow the IPSO to determine the best size for DGs. We want to see if there is any improvement towards the power loss reduction and voltage deviation when we allow the IPSO to determine best size. All right. Keep in mind that the total size is still capped at 2,200 kilowatts, and the maximum size for DG is 2,000, minimum is 50. So in here, in the loadflow.m file, we can see whenever the number of DGs is more than 0, which determines how many DGs we're going to use in the system, and when the optimal size is true, the system when it's false, the system will consider constant value for DG size. For example, when the case is 1, we consider 600 kilowatts for the first DG, or the only DG exists in the system. When there are 2 DGs to be allocated, The first one would be 600, the second one would be 500. When there are 3 DGs to be placed, the sizes of DGs would be 600, 500, and 700. So these are just constant sizes of DG size. You can assume any values you want, but make sure you're not exceeding the total size of 2,200 in this case. So at the end, the DGs are basically added to the buses, and the real and reactive power are added into the bus system. So let's go to the test 4, where we going to allow the IPSO method to determine the DG size as well. So in this case, once again, we're going to consider the best locations of EV charging stations, and you can determine how many DGs you want to have in your system. And as you can see, optimal size is set to true. So in this case, when the size is true, the size of DGs are basically allocated with a variable called DG size. So the DG size is just the array, and the first one is for the DG1, the second one is for DG2, and the third one is for the third DG. So in the IPSO code, there is a section regarding to load flow, and as you can see, when the number of DGs are not equal to 0 and the optimal size is true, DG size is being selected from the SC_DG index, one of the indexes that is determined by the IPSO, can determine what would be the size of the DGs here. And that's how the size of DGs are basically picked from the range of 50 to 2000, in this case, kilowatt. So in here, the iteration is set to 100. So as you can see right now, the best cost is again reduced drastically from 137 when there was a constant size for the DG. So once again, you can see the best cost is 99.87. So that is actually an improvement compared to the test tree where we had a constant size for DGs. Once again, the EV charging station locations are same still, 2, 3, 6, 7, 13. And we can see that once again, the DG locations are selected as 6, 13, 7. And these are the sizes that the IPSO decided to consider for the first, second, and third DG, which definitely is not as the constant size. As you remember, constant size was 600, 500, and 700. And here we can see that the power loss compared to no DG, this is compared to no DG result, all right, is basically reduced by 310 kilowatts, and that's 76% improvement. So when we look at the voltage profile, we can see that the minimum voltage is 0.93 and the voltage deviation is 3.84. And compared to no DG, this is almost 21.53% reduction, which is around 84% improvement. So the voltage deviation and power loss states that this method is helping the system to reduce the power loss a lot and voltage deviation significantly. So this is the end of the test, the 4 tests that we had. For the EV charging station configuration, you can go ahead and select, consider any different charging, number of charging points you want. You can even change the number of charging points you have. Let's say you may consider 8 of charging point 1, 3 or 4 in charging point 2, and even 0 in charging point 3, and still this program works. Or even you can change the output power. All right, if you have a certain charging point that gives you a different power than this, you can change the numbers. Go ahead and change the number as the charging point you have and the power loss and the real power and reactive power calculation would basically follow the same. Or if you want to have different power factor, you can even change the power factor of 0.85 to any number that you think is good to have. So we can take a look at the line data and bus data. This is the line data of IEEE 33. This is the standard values that the IEEE provides for the 33 distribution network. So you can freely use it, and it's going to be same as long as you're using IEEE 33. And one more thing about the EV charging stations, which I told you at the beginning of this video, why we select DG EV charging stations to be at 2, 3, 6, 7, 13. And as you remember, I told you about the test limit. I mean, how many times you can run this test to find out what would be the best EV locations. So in here, the test limit was 1. You can set it to 5. You can set it to 10. And when you determine the test limit, that means you want to have different, you want to test this process for 2 or 3 times or 5 times to find out whether the EV charging station location would be the same or it will change. Because there might be some small changes from one bus to the other bus for the first EV charging station or second one, and you might get different results. Even though I'm running in my computer right now with 3 limits, with 3 tests, you might get different results than I get, but it would be same if you try to get the mood of the locations. What I mean of getting mood is that if you run this test for, let's say, 10 times, you would see that the most repetitive bus locations would be 2, 3, 6, 7, 13. So these are the locations, as you can see right now here. 2, 3, 6, 7, 13 is the most repetitive bus locations that it has. Now you might say why it is not same. It's because the optimization method like PSO does not look for all the answers. It doesn't basically give you, it doesn't search all this space to find you what are the best locations. So sometimes it gives you the results as 2, 3, 6, 7, 13, and sometimes the first bus or second bus would be different. But still, the goal is to reduce the fitness value. And as you can see here, sample 1, I guess, has the highest fitness value, which is not good, but the other samples are perfect. And as you can see here, 2, 3, 6, 7, 13 is repeated 1 time. In here, 2, 3, 6, 7, 13 repeated another time. But in this test, the first DG is the first EV charging station is placed at 19, bus 19. But again, in the first test, we can see 2, 3. Instead of 6, we have 24. So we can see out of 4 tests, 2 of the tests resulted in 2, 3, 6, 7, 13. So that's why we let the system to have these 5 locations as best locations for the EV charging stations. So when we go to the 3rd test and 4th test, we can basically do that. We can let the system to go ahead and at the same time find the location of the EV charging stations and also DG location and DG size. We can still do that, but it's best to consider constant, same locations for the EV charging stations as I did in the 3rd and 4th test to be at 2, 3, 6, 7, 13, and see what would be the effect of adding DG and considering to letting the IPSO to determine the size and location at the same time. So I hope you understand what I said in this part, because it is really important to consider that. Let's say if you run the system 2 times, if the locations of EV charging station changes in one test compared to the other one, so how can you say that adding DG size and location was good or perfect? So it's better to have some common ground in here. Thanks for watching this video and hope you enjoyed it.